Hey everyone. All right. So I feel like this is a good day to kind of put everything together. The entire first derivative test, looking at the second derivative, understanding concavity, finding all the intervals the way we're supposed to, looking at each graph and seeing how they all relate to each other, all that. So I'm going to go through everything. This is going to take a little bit. When you do your example, you don't need to go quite as take as long as me, but I'm going to do it so you have something to refer back to, because all of this is a pretty big theme of first semester calculus. It's being able to have a function and analyze every facet of it. The reason we want to be able to do this is because we use functions to model all kinds of real world behavior, from business, profits, if you have a function that analyzes profits, or in physics, if you're analyzing anything that's changing, position, velocity, acceleration. In chemistry, if you add a catalyst to a solution, how does that change the whatever's going on, maybe the production rate of the solution? I don't know. There's all kinds of different stuff. There's all kinds of different places where you use a function to predict and model what's happening in the real world. And calculus allows you to do a lot more analysis in terms of how the thing is changing as time goes on. Real world example would be, for example, if we talk about an inflection point in the rate of infections of coronavirus. When we hit an inflection point, that means we're no longer increasing at an increasing rate. We increase at a decreasing rate, which would be a good thing, because cases are probably still going to go up for a while. But if we hit an inflection point, that would be where we start to slow that growth. So all of this stuff is pretty important depending on what field you go into. So we kind of just handle the basics of it. And sometimes we can forget that it's all tied to other things. And this is just we're looking at just the math of it right now and doing the calculations, but we build on this stuff in all the different fields, and it gets to become a pretty big part of a lot of different areas. All right, so that was my little 2-minute intro. The function I want to look at is we're going to go through a complete analysis of this function. I gave you a polynomial. I myself am doing a polynomial. So at the end of the day, yours is going to look similar to mine. Different numerical values, but the process is all there. And then we can just apply this to all different types of functions. So it's a cubic. It's polynomial. It's cubic. Some things you could talk about, pre-calculus type stuff, like before you know all of the cool calculus stuff. So some pre-calc basics. Just things to remember. Domain's important. So I could ask you about domain. This is a cubic. It doesn't have any weird spots in it or anything like that. No asymptotes, no endpoints, no holes, no jumps or anything. So the domain is just negative infinity to infinity. It's pretty much the case for most functions. The range, well, since it's a cubic, it goes all the way down to negative infinity, all the way up to infinity. So the range is also all real values. But good to remember that domain and range sometimes play an important role. Some other things you should be able to tell me are the roots. Roots, well, this is a cubic. It's harder to find the roots of higher degree polynomials as opposed to quadratics. If it was quadratic, we could do the quadratic formula or factor. If it's a cubic, you could try to factor, which is tricky. You don't need to know this, but I just will remind you of something you can always try called the rational root test. I cheated and I know 8 is a root, but if you know one of the roots, you can do synthetic division and actually go through this whole process. If you don't know what I'm doing, I'm not going to really explain it right now because it's not an essential part of the course. But that allows you to factor down a little bit. X minus 8 times negative x squared minus 3x plus 1. So I know 8 is a root. Hello. And I know, well, whatever I get here, I could use the quadratic formula, which I'm not going to do. We can look at the graph for that. But I know 8's a root. It went in. I got this 0 remainder. If you had me in years past, you've seen me do this little happy face. That means there's no remainder. Do you have to do that for this course? Not really. That's more of a pre-calc integrated 3 topic. Other things you could do for this problem is tell me things like the y-intercept. So y-intercept, you just plug in 0. Always remember you plug in 0 to get the y-intercept, and it's negative 8. So cool. We know the y-intercept is negative 8. Finally, in this kind of pre-calculus list of things you can do, you could tell me the end behavior in both directions. We do that by saying the limit as x approaches negative infinity of my function is something, and the limit as x approaches positive infinity of my function is something. Well, there's no asymptote, horizontal asymptote in this, it's polynomial. It means it's going to either do this, 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 or this. It's one of these, okay? Because it's cubic, meaning there's opposite end behavior. If it's even power, quadratic, it goes like this or this. All kinds of old pre-calc stuff coming back. How did we learn to find it in this class? Well, if it's a negative, just plug in a big negative and look at the biggest degree. So really, we just need to look at what's happening with the x cubed term if I plug in a negative. A negative cubed is negative, and negative times a negative is positive. So in this direction, it's positive infinity. In the other direction, it's negative infinity. We did that in this course, but technically that's a pre-calc topic. And then one other thing we could always talk about, there are no points of discontinuity. We already kind of said that here. So no points of discontinuity. If there was an asymptote or there was a hole or something, we would have included it in this part. No points of discontinuity. So we're working with a pretty typical function. That's the case most of the time in calculus. We deal with a pretty typical function that nothing much crazy is going on. We don't really have weird jumps or things like that. All right, so now the second thing we can do is we can find the critical points. We're going to determine where the function is increasing and decreasing. And we're going to classify those critical points using this. All of this is known as the first derivative test. So we're going to complete the first derivative test. I have given you a nice function on purpose because this is mostly to highlight all of the important processes we're going through. I'm not focused on finding a difficult derivative right now, but you should be able to find the difficult derivatives no matter what we have to use. Product rule, quotient rule, chain rules, all that stuff comes into play here. So the derivative is not too bad. Power rule, negative 3x squared plus 10x plus 25. Okay, I'm actually going to come back down here and zoom in. We have our derivative. I am going to factor this. I like to take out the negative. So if there's a leading negative, I gave this one to myself on purpose because I don't like negatives as a leading coefficient. So I'm going to factor out the negative just so I don't mess myself up. And now I'm going to factor. I believe this factors as negative in front, a 3x and a 5, an x and a 5. This one's got to be negative. This one's got to be positive. So there's my derivative, factored, which means based on what you guys did, this is kind of where I started you on your last video, you get two critical points. You get x equals negative 5/3, and you get x equals 5. These are your critical points. So now we can do the first derivative test. Label your number line because as you now know, there are going to be two of them, negative 5/3 and 5. I'm going to test something in this interval. You don't actually have to show me what you're plugging in anymore. We've done a lot of that, but for this purpose, I still will. Test x equals, somebody in theirs chose a really giant number like 10 or 100 or 1,000. I kind of like that. Choosing one like 6 means I have to think harder than I want to. But if I choose like 10 minus 5 is positive. 30 plus 5 is positive. But then look, this negative in the front kind of flipped everything. So it really is negative, which means the function decreases. Plug in something right between. I love plugging in 0. I get a negative, I get a positive, but then another negative, because that negative I factored out in front. It's increasing. And then the last interval, if I plug in like negative 50, I get a negative times negative is a positive, but times this other negative is a negative, so it decreases. So what are you telling me here? Well, you're telling me the function increases in the middle from negative 5/3 to 5. It decreases from negative infinity up to negative 5/3 and 5 to infinity. And we can classify. I'll classify on the number line. This is clearly a relative max or local max. This is a relative min or a local min. Same thing. These are called the local or relative extrema. Extrema means extreme points. So a max is an extreme point, a min is an extreme point. These are called the relative or local extrema. Okay, we won't look at the derivative graph yet. We'll come back and look at it at the very end, but we should definitely always remember we can look at the derivative graph and see if things are working the way they're supposed to. Okay, so now that we've done that, we can move on to the third thing that's new, where we can find the inflection points. Inflection points are where the function changes concavity. We can find our intervals of concavity. And we don't really classify them because inflection points will always be a point where we change from concave up to concave down or vice versa. This is not called the second derivative test. The second derivative test is something else that we're not doing right now. So don't worry about it. It's not called the second derivative test. The second derivative test is another way to talk about classifying points. So it's not called the second derivative test, in case you were wondering. So we need to find the second derivative. Second derivative means just do the derivative of the derivative. I think it's easier to go and start from this point right here. So rather than try to do the product rule, which you can, I'm just going to do the power rule on the multiplied out term. So negative 6x plus 10. Which means this is pretty nice. It's linear. I can just set this equal to 0 and find my inflection points. So set this equal to 0. And I get an inflection point at 10/6 or 5/3. Now, this was negative 5/3 for relative min, and this is 5/3. That's interesting, but there's a little something going on there, but no, it's coincidence in this case. It does happen that if you have a cubic, the inflection point is halfway between these 2 points because of the symmetry. So yes, the fact that we had an inflection point at 5/3 because it's halfway between these two is a thing, but we're not going to talk about that right now. Okay, if you didn't get that, don't worry. Let's make our number line for the second derivative. 5/3 is on it. You only have 2 intervals to test. If I am bigger than 5/3, it looks like I am negative because I get 5/3 times negative. Like let's plug in 50. 50 times 6 is a giant negative. Adding 10 is not going to help. We are concave down. Make the entire thing. I don't care if it's increasing or decreasing. Just put this concave down shape, like an N. Someone called it an N. I don't. Okay, I guess. In this section, we are concave up. If I plug in 0, I get a positive. So we have our inflection point where we change concavity. We either went from Mullen to Yip or Yip to Mullen at that spot. And when we look at the graph, we'll see. So we have our inflection point at 5/3. We are concave up in the interval negative infinity to 5/3. And we are concave down in the interval 5/3 to infinity. Okay. All right. So that's all of the kind of talk of how this function is behaving. Now putting all of this together, everything here gives you a good picture. Everything should match up, first of all. So little things like the end behavior, when I say we're going down, 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 down to negative infinity, look how that matches up with this piece right here, telling me that I am decreasing. That makes sense. It also matches up with the concavity. If I was concave up decreasing, that would be like leveling out. That'd be a horizontal asymptote. So there's a lot of, all of this should make sense together. One of my pet peeves is when you tell me 2 conflicting things within the same problem. That means you know you did something wrong. End behavior should match up with how I'm decreasing, should match up with my concavity. I should be going down at an increasing rate. Okay. So we'll learn how to do all that stuff when we go through the more curve sketching side. But some of you guys did a really good job of curve sketching. So I'm going to call this part 4, and I'm going to try to put all of this together. So part 4, putting it together. One way we're going to learn how to do this is we're going to turn and put everything on the same number line. This gets challenging if you start to have a lot more critical points and inflection points. But check it out. In this case, it's not so bad. I can put negative 5/3, which was a relative min. I can put 5/3, which was my inflection point. I can put 5, which was my relative max. Now, you ready? I'm going to try to look at both number lines at the same time. So when I was left of negative 5/3, I was decreasing and concave up. So I kind of had this shape. From negative 5/3 to 5/3, I'm increasing and still concave up. So that's where this shape came in. From 5/3 on to 5, I'm increasing just like I was, but I switched concavity. Now I am concave down. So I am this type of thing. I switched from a yip to a mullen. And then finally from 5, I am decreasing concave down, something like that. So that would be putting it all together. And then you could put that into a curve sketch where you kind of connect all the segments. Some of you guys did a really good job of this when you did your last video. I don't know where it's located. So if I really did try to put it on an actual graph, you know at negative 5/3, which is here, we'll say this is 5/3 and we'll say this is 5. All you know is that the graph is changing at these spots in the ways as we said above, but you don't know if the graph is like way up here or way down here or somewhere in the middle. So you just kind of sketch it in the middle is a good usually rule of thumb. So I'm going to do this. Graph's going down, 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 down. But then you can start to use other information. I may as well do this right. You can use other information like I know that the y-intercept is -8, so I know it has to cross way down here. So I may do something like, okay, I know it goes way down here like this, levels out, then it goes up, 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 up. We hit our inflection point, so we switch from yip to mullen. We hit our max at 5, and then we go down. So maybe something like that. If I really wanted to use all of this other information like roots and all that, I could get a better curve sketch, but this is fine for now. I don't really care where it's located. I only was picky because I have the graph right here, so I know exactly what it looks like. All right, and finally, there is my entire analysis. Let's see and make sure that it matches up the way it's supposed to. This is probably the most important part, because if you're doing wrong work, you're not gonna lock in how to do this whole process correctly. Ready? So here's what the graph looks like in Desmos. Some of you guys are doing a really good job of pulling up Desmos and looking at it. By the way, some genius told me, really smart guy, to change my scaling. So look, I changed the Y scaling to 50, 100 because these things tend to get really stretched. So don't be surprised that mine looks so clean. I changed the scaling. You should too. How do you do that? You click the little wrench and go down here to Y axis. You change the scale. I would make it like -100 to 100 and then go from there. Okay, how did we do? Did I actually have a root at -8? I did. There it is. Was my end behavior correct? It was. I went up to infinity as I went that direction. I went down to -infinity as I went in the positive direction. Is my domain and range looking good? Yeah, that part wasn't too astounding. Okay, ready? Did I have a relative max at -5/3? I did. There it is. Did I say relative min at -5/3? Did I have a relative max at 5? I did. If I wanted you to find those y coordinates, you could always plug these into the original function and get the y coordinates. Usually I don't ask for that. It's kind of overkill. Did I determine where I was increasing and decreasing? Yeah, look, the function's decreasing until this critical point, then it increases until this critical point, and then it decreases for the rest of time, just like this is showing. So everything matched up. How about my concavity? Was I concave up? Up, up, there we go. I was until somewhere in this range at 5/3, which is like 1.6. Then my rate of change flipped from increasing at an increasing rate to increasing at a decreasing rate. I'm slowing down. I went from a yip to a mullen. Okay. I like using that terminology because it means I went from increasing at an increasing rate to increasing at a decreasing rate. And then I leveled out, and then look, I'm decreasing, but at an increasing rate. Well, technically it's decreasing at a decreasing rate. We're going to get into all of that when we get to motion. If the first derivative and the second derivative have the same sign, it means you're speeding up kind of in the reverse direction. So yes, I am getting steeper, 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 steeper because both my first derivative and second derivative are negative. That'll come later. Okay, so just for now, notice your concave down. That's what I really want you to notice, the concave down. And how does it look? My curve sketch looked decent enough. Yeah. One last thing I want to remind you of is if I look at the derivative graphs, so here's the function I gave you, but if I look at the derivative graph, y equals negative 3x squared plus 10x minus 25, negative 3x squared plus 25, sorry. This should match up. Start getting in the habit of doing this, okay? So check it out. The green is the derivative graph. And yes, the derivative is a, I'm going to cover this. The derivative is a parabola because you decrease the degree by 1. We had our critical point at 5. There's the root at 5 of the derivative. Ready? The roots of the derivative are the critical points of the original function. Before it, I was above. I had a positive derivative. See how the derivative was positive values and then switched to negative values? That means in the original function, I went from increasing to decreasing. Same thing at this root right here. This root matches up with this critical point. Same value. The graph went from decreasing to increasing, which means the derivative graph went from below the x-axis to above it, from negative values to positive values. Okay? We can then also apply this to the second derivative. Ready? Negative 6x plus 10. So some of you guys notice that it's a line. In this case, it's a line because the second derivative goes down by 2 degrees. So check it out. What is this telling you about the original function? Well, at this point, we have our inflection point. Before it, we were positive in the second derivative, which means we were concave up. Right here, when we flipped and went negative, when the second derivative was negative, meaning below the x-axis, the graph was concave down. So the goal of all of this, most of the time, they start you right here with the second derivative and ask you questions about the original. So based on how this function is located and where it's increasing and decreasing, you should be able to answer questions about the original. So I'm hoping you caught on something pretty cool here. If I look at this derivative graph and see that I had a critical point right here in the derivative, the critical point of the derivative is the root of the second derivative is the inflection point of the original function. So right here, this root of the second derivative matches the critical point of the first derivative, matches the inflection point of the original function. Those are the connections we're going to have to start making. Okay, we go through this very carefully with all different types of functions, but refer back to this video if you ever get stuck on all these ideas. Okay, it's nice to see it all in one example. And yeah, it's a 23-minute example. Yours does not have to be that long. This is all we're doing. I want to make sure you have these kind of terminology locked in. Okay. And just make sure, one more thing before I'm done. Whenever you're talking about these things, don't say the graph. Start to get in the habit of saying the graph of the derivative, or the graph of the original function, or the graph of the second derivative. If you just say things like the graph or the function, I have no idea which one you're talking about. So now we're in a world where you have to start saying the derivative, the second derivative, the graph of the derivative, the graph of the second derivative. All of that's going to be pretty important. Okay? So hopefully you can get something like this and go through it for yourself. And I wish you the best of luck.